So I'm one of the Jetty guys. So how many of you use Jetty here? Oh, cool. Good part of it. Cool. So, but today I'm here to talk to you about garbage collectors because there's a passion of mine. So let's dive into garbage collection. So this is an introduction about what's currently available in the hotspot JVM. The first collector that was implemented was the parallel collector. It works using two generations, and it uses stop the world algorithms for both the young generation and the old generation. So stop the world means that when the garbage collector decides that it is time to do a garbage collection, it stops all the application threads, then starts all the garbage collection threads. The garbage collection threads will do the garbage collection, and then when the garbage collection is finished, the application threads will be restarted. This means that during the garbage collection time, your application doesn't run. And if the garbage collection pause is very long, then your application will not run for a very long time. This is a problem for a certain set of applications, and therefore we would like to reduce these pauses and try to have algorithms of garbage collection that do not stop completely the world and stop completely the application, but actually can perform garbage collection concurrently with the application. So parallel is not one of these collectors, very good for throughput, but has pauses. So to solve this situation, another garbage collector was introduced. It's called the Concurrent market sweep collector. Also works over two generations. The young generation is still collected with the stop the world algorithm, but the old generation, which is where you most of the time spend the most time during garbage collection, is now collected concurrently. The big problem of this particular garbage collector is that when it has to collect dead objects, so garbage, in the old generation, it doesn't really compact the heaps. So the objects that remain alive do not get moved. And so you run this collector for days and months and whatever. What happens to your old generation is that it becomes like a big, giant Swiss cheese. It's full of small holes. So if you sum the space of all the holes that are in there, you actually have a lot of space. But if you are trying to allocate, for example, a very large array because you received a very large JSON payload, then you may not have the contiguous space necessary to allocate the byte array that is necessary for the JSON payload. So at that point, CMS falls down into a full garbage collection, and that's really slow again. So the big problem for CMS is fragmentation. So in order to solve the fragmentation problem, another garbage collector has been introduced. It's called Garbage First, G1. Also works on two generations, also still does the young generation as a stop the world algorithm. The old generation algorithm has been a mixed way of things. The marking of live objects is actually done concurrently, but the compaction of those objects is actually done in a stop the world pause. The good thing and the difference with the parallel collector is that the old generation gets split into multiple pieces, let's say, and then only one piece at a time gets compacted. So instead of having to compact the whole old generation in one step, we split the work into multiple passes, and we try to recover as much space as possible during the first passes so that we have more free space to let the application continue its work. So it is better than the parallel collector with respect to pause times. However, still has this problem that the young generation and the old generation compaction is actually a stop the world phase. Well, in order to fix the problem, finally, two new garbage collectors have been introduced very recently. One is called ZGC, and the other one is called Shenandoah. They work on a single generation, so they use the heap as a one giant generation, but they are able to do concurrent marking and concurrent compaction, which is a feature that the previous garbage collector couldn't actually do. So these new collectors are very exciting because they promise very, very short pauses for your GC, and therefore they will eventually solve what is called the garbage collector problem, which is I don't want to stop for a lot of time with my application completely stalled because the garbage collector is running. But they are concurrent garbage collector, so they run together with the application. And what happens when you have two threads running at the same time? You have race conditions. And so this is very typical for this garbage collector. They have to solve this problem. What happens if the garbage collector is actually moving one object into another place, but then the application is still accessing the place where the old object was before? Well, you could have a lot of problems. You can have you can lose data, or you can even have a JVM crash, because you're now accessing some portion of memory that is not good anymore because the object has been moved to another place. And so these collectors have to resolve this problem, and we'll see in a moment how they do it. So this is the actual problem. So we have here two regions, and we have one object pointing to another object, okay? And the garbage collector comes in and says, okay, I want to compact things. So it copies the object, in this case, the one that is in the second region, to a third region, which is empty, and so it compacts all the live object into this new region, right? And so a bit of terminology here. When an object is being copied, it is said that the copy the object that you are copying is called the from space copy, and where you're copying the object to is called the to space copy. Okay, so I will use this term in the next slides. So the garbage collector has now copied the object, right? And then exactly at this moment, the application comes in and says, okay, now I want to write a new value for the field of this particular object. And so it writes the value 3 in the field of the object, right? The garbage collector, however, is not finished. It says, well, okay, now that I have moved the object, I need to update the reference from the first object, now has to point to the new location of where the object is, right? So I need to update that particular reference so that in the future, I'm going to this new place where the object has been compacted. Well, I just lost a write. Okay, the value 3 is now completely lost. It has been written in the old object. That's not good. So we'll see in details how this problem is being solved by both ZGC and by Shenandoah. The basic strategy the concurrent garbage collector used to solve this problem is twofold. The first one is to store some additional metadata about either the reference or the pointers that mark the object itself. And then they require JIT support. They require that the JIT injects a little bit of garbage collection code that helps the garbage collection to figure out what state is that particular object, whether it should be moved, whether it needs a particular treatment, whether it needs to be processed in a particular way. So by injecting this little bit of code, we are taking care of this concurrency problem, all right? What is the problem of this additional code, GC code? It costs, right? It is CPU cycles that we are actually spending running GC code and not application code, right? So we have a throughput hit when we run these barriers. The advantage, though, is that we have an algorithm in the garbage collector that can be very efficient. So this additional GC code that is being injected by the JIT is they're typically called GC barriers. Let's dive into the details of how ZGC actually works and what ZGC actually is. So ZGC is a project from Oracle. It has been introduced in JDK 11, and it is available in Adopt OpenJDK builds, and I guess from many other vendors, and it's also available in the Oracle binary builds, downloadable from jdk.java.net. It is a scalable low latency garbage collection, as I said, does concurrent compaction, and it uses a single generation. The major drawback for ZGC is that it is only available for the Linux 64-bit platform. There is an ARM 64-bit port underway, but that's the only basically platform and CPU combination and architecture that you can use for ZGC. Not only that, but if you're working with small heaps, you cannot use compressed pointers, and we'll see in a second why. ZGC is based on what they're called regions as well. Pretty much anyone here is familiar with regions. G1 uses region. ZGC also uses regions. They're slightly different from G1. They're called Z pages, and they come in 3 sizes. But typically they just can be assimilated as normal region as you're familiar with the G1 ones. So let's look at how ZGC works. So when it starts a garbage collection, there's an initial phase, still stop the world, okay? During this initial phase, the garbage collector has to collect the root of the object graphs because it needs to navigate all the object graphs. So it scans all the threads because local variables needs to stay alive. So goes through all the threads and say, okay, this is a local variable, it is a GC root for me, right? And so on, collects all the GC roots, and then it has to stop the threads to do that because I cannot have a thread running and changing local variables while it's collecting the roots. Once the roots are collected, that stop the world phase is over. And now the garbage collector can do concurrent marking. Okay, it can run through the object graph and navigate in the whole object graph concurrently with the application. While it is doing that, the garbage collector, it is acquiring a lot of information. First of all, it is navigating every live object. And by navigating every live object, is also able to gather liveness information for every single region, okay? Because, for example, imagine you have a region that it contains some object. I have a located object in that region. But during the marking, I never enter that particular region. What does it mean? It means that the region is just full of garbage, okay? I have allocated a lot of stuff in there, but then nobody is referencing that, the objects in that particular region. And therefore, I know that the region is completely full of garbage. Not only that, it also, navigating the object graph, collects information about the weak references, soft reference, etc. The other phase that follows this one is another stop the world phase where ZGC is actually finishing the marking, and then it is doing some housekeeping. It is preparing internal data structure for additional phases. And it's also flipping the phase of the garbage collection. What follows is another concurrent phase where ZGC does a lot of things concurrently. For example, it performs reference processing concurrently during this phase. It frees the memory pages that it found were empty in the previous concurrent marking. It unloads classes. This is available in JDK 13 or 13, definitely. And it also prepares for the next phase, which is the compaction of the heap, right? So it says, okay, now that I'm doing all these things, I have a lot of information. Let me prepare all the data structure that I need for the next phase. The next phase comes in, also involves a small stop the world pause, where ZGC is basically say, okay, now I need to compact the heap. The first thing that I want to do is I want to compact and relocate possibly the roots, okay? Again, selects all the roots of the object graph and says, okay, I need to move these guys and compact them somewhere. Once it has moved the roots, it is free to go concurrent again and perform concurrent compaction of the heap. Now, at this point, it's navigating the object graph again, and it is moving all the object into new Z pages so that they get compacted into new pages, and all the old pages can now be recycled. There's one more phase that it's the phase that requires that every object that has been moved, okay, so the other object that were pointing to the old location of this guy, now I have to point to the new location of the guy, right, of the object, where the object has been relocated. This phase is called concurrent remapping. However, it is not run after the relocation phase. It is actually run on the next marking cycle. So it is an action that is being performed not immediately, but when the garbage collection detects, okay, I need to do the next garbage collection, when it does the marking, also updates all the references for the previous marking cycle that has been performed, GC cycle that has been performed before. So navigating the object graph is a very expensive operation because you need to load a lot of memory to navigate the object graph, and therefore that's the reason why marking, which involves navigating the object graph, and remapping, which also involves navigating the object graph, are done together. We will see that this is pretty common in this kind of garbage collector. So now that we know how it works, we still don't know what is the technical detail that ZGC uses to fix this race condition with the application. How does it fix this problem? So it uses two techniques. One is called colored pointers, and the second one is a load GC barrier. These two work together in order to solve the concurrency problem, and I'll give you a concrete example of how this works. So what's a colored pointer? Remember, ZGC only works with 64 bits pointers, okay? However, modern CPU cannot use all the 64 bits to actually address memory. They can only use up to 48 bits. All the remaining bits are unused. So ZGC exploits this and says, okay, I'm going to use 44 bits to address memory. I'm going to use other 4 bits as metadata, so they are Boolean flags, basically, that the garbage collector will use, and then all the other bits are basically unused, okay? So the logic is, if I have some information in the pointer itself, whenever I am navigating or the application is actually loading a reference through the virtual machine, I can look at this pointer, do some masking on the bit, and understand whether that particular reference pointing to a particular object needs to be processed in a particular way by the garbage collector, right? If it has the wrong color with respect to the state of the garbage collection, I need to do some action, all right? The other technique that I was saying is the use of a load barrier. Load barrier is basically this. Every time you load a field or an object from the heap, logically, this is like typical Java code, where you have an object, obj, and you want to load a reference field inside that particular object. Then the JIT injects a little bit of code just after this particular operation that you do in your application, okay? How does it look like? It looks like this. Well, the variable f now contains the reference to the field, okay? What the JVM is doing is saying, okay, let me take the address of that particular reference, so it gets the actual pointer value, and I'm going to do an AND operation with the wrong color, because I want to know whether if that pointer that has the colored bits has the wrong color, all right? If it has the wrong color, then I need to do an action, and therefore I need to take a slow path, okay? In assembly, it looks like this. The RDI registry contains obj. I just move 16 bytes forward, 0x10, to get the field, and I load the field into the RSI registry, okay? And then comes the load barrier. The R15 registry contains some thread local metadata related to the garbage collector, and I just move 32 bytes forward, that particular data structure, where I have the bad color, right? And I load that. And I want to test the RSI registry that contains the reference, the pointer to the field with the bad color, all right? If it's not good, it's a wrong color, I want to jump to a slow path, okay? So it is very cheap, and now you understand to do this operation, because it's only one operation, a test, that gets done over and over again every time you need to load an object from the heap with the semantic, right? So that's the reason to use color pointers, because if I have the information exactly in the pointer, then the load barrier becomes very cheap, all right? This load barrier has been measured by the ZGC team to have an impact of about 4% on normal usage. So it's not free. It has to be as cheap as possible. So one solution was, well, let's encode some metadata in the pointer so it will be super cheap to have a load barrier. So, well, the slow path has to do what then? So I discovered this reference, I'm testing the color, is the wrong color, I need to go for the slow path. Well, the slow path has to do two things. Has to fix the color of the pointer, and then has to take some action. And that action needs to be atomic. Because if it is not atomic, then I have a problem, a race condition with the application threads, right? The action that needs to be taken depends on the phase of the garbage collection. So if I'm doing marking, I'm going to do some action. If I'm doing relocation, I have to do some different action, and so forth. There's one little glitch, though, of using colored pointers. So if you change the bit of a pointer, what happens? Well, if you look at this diagram, you see that if you have a pointer that says 001 and then some address, then I am in a certain region of the virtual memory. But if I use the colored bits and I change them and becomes 010 and then the same address as before, I am in a completely different region of the virtual memory, and so forth, right? So the trick that ZGC uses to avoid that we have problems with this is the following. It maps the same physical memory into 3 different virtual memory regions, so that basically the color bits become completely influential at this point, right? I can use the same pointer, it will go through virtual memory, but eventually will point to the physical memory to actually get the value. And so in this case, I will be able to put metadata information within the pointer itself. For example, the ARM processors do not need this triple mapping because they are able to actually load the reference and also do some masking so that the color bits get the information about the color bits, it becomes irrelevant. They'll be colored out, I would say. Is this, why am I even mentioning this? Well, I'm mentioning this because turns out that the resident set size that is displayed over Linux for the report of how much memory a process is actually using reports now a 3 times more memory than your process is actually using. Is this a bug in RSS reporting, or it is a bug in the tools that actually go and look for the RSS value rather than using a more interesting value which actually report more correctly the actual memory used by the process? Well, there's many opinions about this, but it is certainly a problem that you have to take into account if you're using ZGC. If you're using ZGC on the cloud, for example, there are OM killers that will kill your JVM because it will think, oh, you gave this process a maximum of 16 gigabyte, but 16 times 3 goes to 50 gigabytes, and because your process is using 50 gigabytes now, I'm gonna kill it, and your JVM, it's killed immediately. So watch out for this. You have to do some, you need to be aware of this feature of ZGC. And now we go into the example where I would like to show you what happens with relocation and how the color pointers and the load barrier work together in order to solve the concurrency problem, okay? This is an object graph. Starts from the root object A and then goes down into children's. And the garbage collector decides, okay, it's time to do a collection, and I've already done marking. I want to relocate this object graph. So it starts from the root A and says, okay, the root A doesn't need to be relocated. It's already well compacted into a page. Let's leave it there. But then it navigates to the children and finds object B and says, okay, B needs to be relocated. So what it does is it copies the object into the to space in a new page, but then stores on the side metadata that says, okay, object B, the address of object B, now is on B prime, all right? And the same does for object C and object D. As you can see, the pointer still point to the old places of the objects, all right? Then the garbage collector is about to move to the upper side of the object graph, but exactly at that point, the application comes in and wants to work on object E, right? And so at that point, the application comes in, has to load the reference for object E, compares the color, and it sees that the color is the wrong color. And therefore, the application thread has to take the slow path. What is the current state of the garbage collector? Well, the garbage collector is doing a relocation. Therefore, the slow path has to relocate the object. And this is done by the application thread. Okay, so the application thread does a little bit of work that the garbage collector is normally doing. It is copying the object and relocating it into a new page. Okay? And then, of course, the application stores the information about this relocation into the metadata that is on the side. There is basically a concurrent map. Exactly at that moment, when the application thread is doing all these things, the garbage collector arrives. What happens? The application hasn't finished yet, but the garbage collector goes in and says, okay, what is the color of this pointer? It's the wrong color. Okay, what is the phase of the garbage collector? It's relocating. Okay, I need to relocate this object. And so creates a second copy of the object, E2, here, and tries to insert that information into the concurrent map of the metadata. But it cannot do that because it finds out that for the key pointing of the address of E, there's already an entry. Okay, so that's a concurrent put into a concurrent hash map, and therefore one of the two will win and the other one will fail. Okay, so at this point, the garbage collector figures out, I've been beaten at relocating this object, therefore I need to discard my copy, discard what I was doing in the relocation map, metadata on the side, and I need to take that information that has been put in there and then use that as the prime information about where this object is now, okay? Then the application is done. Maybe it was just accessing object E to read some value, but it was not really following any pointers from object E. Therefore, the garbage collector has to continue and continues on and then goes to object F, relocates the object, inserts the information into the table on the side, and we have done the whole relocation step is now finished. And so you can see that colored pointers with the load barrier with an atomic action, which is the insertion of this relocation information into a concurrent hash map on the side, is the mix that allows ZGC to actually resolve the concurrency problem with application threads. It also asks, the load barrier basically asks the application threads to say, hey, if you trigger and you have to take the slow path, then the application thread has to help the garbage collector to do a little bit of work, okay? So think of this as you walk around the house, you know, there's some stuff to clean, and then as you walk along, you see maybe a sock on the floor, and you say, okay, let's pick up the sock, and you put the sock away, right? You are doing things, but then the next day someone else comes in and clean the whole house, but that particular sock is already, you know, put in the right place because you were walking in the house and you did a little bit of job. So the next phase is the remapping phase. As you can see, the garbage collector navigates the object graph and then fixes all the pointers to the new location. So now the object A now points to E prime and not anymore to E, and so forth for all the rest of the graph. Therefore, at this point, it's again a consistent object graph, and you know, it can be navigated again for marking and so forth, can be used by the application, etc. So this is how ZGC works. Here you can find a few references. The team that is working mostly on ZGC are Per Liden and Erik Österlund, and they're located in Stockholm. You can find a few YouTube links to their presentation where they go into more finer details about ZGC. There's a wiki, there's a mailing list. I suggest that if you have any problem with ZGC, you subscribe to the mailing list. They're very quick to reply. I got a ton of help to trying to understand how ZGC was working, looked at the code, but then asked questions on mailing list, reported a few bugs, and you know, they're super kind, super helpful. So enough for ZGC. Let's move to another collector, which is also very interesting, which is called Shenandoah. Shenandoah is actually a project from Red Hat, and it is being merged in the OpenJDK 12 source repository. This means that if you are building OpenJDK 12 or later, you will get Shenandoah if you're building it yourself. Adopt OpenJDK builds contain Shenandoah. Oracle builds do not contain Shenandoah because, well, it is a Red Hat effort. And of course, Oracle, rightly so, says, well, I do not want, you know, this contribution from outside, because if people has problem with Shenandoah, and they have downloaded my OpenJDK, then, you know, they will come to me asking to fixing things, and, you know, this is not my project. So Oracle's builds do not contain Shenandoah. So be aware of that. If you really want to use Shenandoah, your choice is to use some other vendor that is not Oracle that provides Shenandoah. The good thing about Shenandoah with respect to ZGC is that because it is derived from G1, it is available for all architecture, 32-bit, 64 bits. There are ARM ports available. It is available for Linux, Mac OS, Windows. You can use compressed pointers, but not only that, I have to really say that Red Hat did a wonderful job on this. They are backporting very actively the Shenandoah garbage collector from the current development, which is JDK, let's say 14 and 13. They're backporting it back to JDK 11 and also back to JDK 8. Okay, poll question. Who's still on JDK 8 now? No. Many people, but so if you want to use a concurrent garbage collector, then Shenandoah is basically your only option. ZGC is only available JDK 11 plus. So either you migrate or you take this as a choice. The phases for Shenandoah are quite similar to ZGC. Stop the word, mark start. Again, scan the threads, find the roots, from local variables and everything, and mark all the roots. Then you can proceed and do a concurrent marking. Marking the object graph, again, discovering all the Java-lang references, gather liveness information about what regions are more, have most garbage or even completely garbage. And then there's a stop the word mark phase at the end of the marking where Shenandoah does a lot more things than ZGC. So in this stop the word phase, Shenandoah is processing the weak references, which ZGC was actually doing concurrently in the next phase. But this is now done in a stop the word pause. So this pause is likely to be a little bit longer than what is the correspondent pause in ZGC. It does class unloading, which also ZGC is doing concurrently. It evacuates the roots, and then it does housekeeping to clean up and prepare internal data structure for the next phase. The next phase is concurrent evacuation. This is the same as relocation, as it was called in ZGC. Basically, it is heap compaction. Okay, this is where Shenandoah moves all the object into new regions in order to compact them, so that the old regions where it moved all the object from can be completely recycled and cleaned up. Exactly like ZGC, once I move objects, then I have the need to fix all the pointers to the new location of where I moved the object to. Remapping phase was called in ZGC. In Shenandoah, this is called the update references phase, but it's basically exactly the same. And exactly like ZGC was doing, the remapping phase and the update reference phase, it is done not immediately, but in the next marking cycle, okay? Because again, I need to traverse the whole object graph. It's an expensive operation. I wanted to be able to do it when, the least number of times possible. So marking is a very good occasion to navigate the object graph. I have to navigate it anyway. Well, why not fixing the previous GC cycle pointers as well? All right, so what's the algorithm for Shenandoah to fix the race problem with application threads? It's different than ZGC. It uses two different techniques. One is called Brooks pointers, and it also uses GC barriers, right? In this particular case, Shenandoah uses load, store, a combination of the two, or we will see just one of the two, because there's two versions of Shenandoah, which I will go into a second. But before I go into that, in order also to explain what a Brook pointer is, I need to explain how Hotspot lays out objects in memory. This is a typical layout of objects in memory by Hotspot. There are, depending on the architecture, the term word means either 32 bits or 64 bits, right? So it's the size of a pointer, basically. So there's two of these in Hotspot before every object. The first one is called the mark word, and it's actually being used as a multi-purpose information storage. For example, this particular set of bits can hold mark information for the CMS garbage collector. It can hold, every time you call system identity hashcode, the hashcode is actually, that particular hashcode is stored in this mark word. Every time you do bias locking, etc., there are bits that are flipped in this word. So it's basically like a metadata information about that particular object. The second pointer word is the class word. It is basically a pointer to the class of this object. Okay. I learned today that OpenJ9, for example, doesn't have two words, it only has one word as object header. This is particularly So this layout is hotspot specific, but OpenJ9, for example, only has one of these two. So now we know how objects are laid out in memory, and I'm going to present you Shenandoah 1.0 and what is a Brooks pointer in Shenandoah 1.0. So this is a normal layout for hotspot, two objects pointing to each other. And this is how Shenandoah lays out objects, Shenandoah 1.0. So as you can see, before any object, there's an additional word. There is a forward pointer. This forward pointer basically has the information of where is the actual copy that it is the valid copy at any time in during the life of this object. Okay, so typically the forward pointer points to the object itself. Okay, but when I copy the object, the forward pointer can point to the second copy. We will see an example in a few slides. All right, so there's an additional word basically before any object, and so Shenandoah 1.0, I'm talking about that because it is still, as of today, the version of Shenandoah that you will find in the JDK 11 and 8 backports. There is a backport underway to take Shenandoah 2.0, which we will see in a few slides, back into 11 and 8. But for now, it's still Shenandoah 1.0. So the key point here is to remember this, that Shenandoah tries to maintain an invariant, which is this. I want to be able to read from either the from space copy or from the to space copy. No problem, because they will contain the same data, right? Up to the point that if I need to write to that particular object, the only copy that I have to write to is the to space copy, okay? Because I know that the from space copy will be destroyed very soon, right? The real copy is the other one. So the weak invariant that Shenandoah 1.0 tries to maintain needs a barrier, right? Exactly as before, we need a barrier. What is it that this barrier is doing? It has to understand and trying to figure out where is the actual copy of the object that I need to, use to read and write values, right? And so what it does is basically this. It is taking the address of the field, has to go 8 bytes before that, where the forward pointer is. It has to load the forward pointer and then follow the forward pointer, right? Typically, what happens is that I go back 8 bytes, and then the forward pointer points to the object itself, and so it goes forward 8 bytes. So it's basically back 8, forward 8. So it's basically like almost an operation, right? But it's needed because if in the rare cases where the forward pointer is not pointing again to the same object, but to another copy, then I need to follow the other copy, right? So I always need to be sure of that. Again, in assembly, this looks like this. The first initial part is the same. The RSI registry contains the address of the field, the pointer to the field. And what I do is I take the RSI registry, I move back 8 bytes, you see, minus 0x08, and then the value that I find there, I'm going to store it again in the RSI registry. So this is what needs to be done every time you load a reference from the heap, right? And so this barrier is always executed. Is it cheap? It is cheap because the key thing is that when I load an object, I not only load that particular object, I typically load the memory that gets moved from the main memory into the caches of the CPU comes in cache lines. And every time I load some kind of object, I load not only that particular object, but I load a lot of space before and after that. So there are very, very good chances that if I move back 8 bytes, that information that I have is already in the L1 cache. And therefore, I will be able to find it immediately. And therefore, this barrier is very efficient again. Not only I need a read barrier, but I also need a store barrier. And the reason for that is, of course, that if I change the object, I want to be able to say, oh, okay, the garbage collector is relocating the object, and therefore I need to understand whether if the application arrives to that particular object first, it is now the application that needs to take that object, move it to a different place, and then write to the new copy. Because otherwise we will end up in a situation that I showed you in the very first slides, where I'm writing to the old copy, to the from space copy, and then when I update the pointer, I have lost the write, okay? So the write barrier does exactly this. It says, am I in the phase of garbage collection where I am evacuating objects? Yes. That's a very cheap Boolean to test. But then, is this object one of the objects that I actually need to move? Because, maybe some object doesn't need to be moved right now. And not only that, has this object already been moved by someone else, by the garbage collector, right? Then if these three conditions actually are true, then the application needs to take a slow path, okay? Has to relocate the object and so forth. We will see an example in a few seconds. This is the assembly for the barrier, write barrier. As you can see, there's again this R15 registry, which is the thread local garbage collector data structure that it is useful. And so I'm going 3D8 bytes forward the beginning of this data structure. Over there, I'm going to see that there is a Boolean that says, what state am I in? And I load this Boolean into the R11 registry, and then I test for this Boolean. Are you true or false, right? And this is, again, a very cheap barrier because R15 is a thread local data structure, and the test is a very cheap operation. It's a single clock on x86. So then, of course, you see the ... You have all the other assembly condition, but they are quite long. You can find them in Shenandoah presentations as well, if you're interested in this detail. So what are the problems of Shenandoah 1.0 and why they went to 2.0? Well, the problem is that the forward pointer takes memory. This means that in the worst case possible, where you are allocating an object that has no fields, then you take up to 50% more memory, because you go from 2 words for the headers to 3 words for the headers, right? And that's 50% more. But this is generally not the case, so typically the overhead is 5 to 10%. But what does that mean, 10%? Well, 10% means that you have to do your garbage collection 10% more times, which means that 10% more times the CPU will be stolen by the garbage collector threads. And therefore, your application will run a little bit slower because some of the cores of your machine will be stolen by the garbage collection, and so forth. So it is a problem. Plus, there was some internal code complications that this version of Shenandoah was struggling with, but eventually solved. But it was still like not the ideal solution. So enter Shenandoah 2.0. Has the algorithm changed? Not really. What has changed is the invariant that they want to maintain this time. And so Shenandoah 2.0 works in this way. When it copies an object, it says, okay, you know what? Before, I was trying to keep the old object kind of alive so that I could read information out of it. But now, nah, let's not do that, okay? Let's just copy the object and let's mark the new copy of the object, the 2-space copy, as the only true master from where reads and writes can actually happen, all right? And well, then turns out that the whole old object can be used to store metadata, because every time I have this object around, then I can just override the object with whatever I want, because every time I'm going to refer to this, there will be a load barrier that will look at the forward pointer and say, oh, this guy is not here anymore, look there. And so every time I will be forwarded to the new place where the new object is, and therefore, I will be able to read and write correctly to this object. Well, what's the good news? The good news is that I don't have the additional word now anymore, so I'm not wasting space like like Shenandoah 1.0 was doing in memory, just to store this particular information. And now this strong invariant allows me this, allows, to simplify a number of things. In particular, what is now has been introduced in Shenandoah 2.0 is to maintain the strong invariant so that the two-space copy of the object is the real primary copy of the object. Then I use this load barrier. How does it look like, this load barrier? Where the first thing that I have to do is, am I evacuating objects? And the second thing is like, is this object one of the objects that I need to evacuate, right? And then has already been forwarded by the garbage collector or by some other thread, right? Are you familiar with this barrier, right? This is exactly the right barrier that was present in Shenandoah 1.0. So the load barrier that it's now in Shenandoah is basically just one. I do not need two different barriers. There's only one barrier, which is the load reference barrier now. And the test is exactly as before. I'm loading now the R15 thread local metadata structure registry. Now the information about where the Boolean that says whether I am evacuating objects or not is 32 bytes forward, the beginning of the data structure, 0x20. And then I'm testing that and say, hey, is the first bit flipped? And if so, then I have to do some slow action. Otherwise, I'm free to continue to load and read from this object or write to this object. We're all good. So again, the barrier is complicated, but the first check that will pass most of the time and fail most of the time is a very quick check. It's just a test operation against a fixed thread local metadata information. Well, now that the barriers are the same, well, I can simplify a lot of the code base. The code base of Shenandoah 2.0 is way simpler. And of course, that comes with, simplicity gets performance. So it was a very good change. So how does it work exactly? Well, this is a normal case. We have an object pointing to another object. The garbage collector comes in and says, okay, I need to relocate this object. I need to compact this object into another region, all right? So it creates a copy of this, right? But exactly at this point, the application comes in, triggers the load barrier. The load barrier says, are you evacuating object? Yes. Is this object one of the objects that needs to be evacuated? Yes. Has someone else already evacuated this object? Well, I'm looking, this is the from space copy, so that means nobody has evacuated this object yet. So I need to do it myself. So it creates a second copy by the application itself. Once it has created the second copy, what is the atomic action that the garbage collector and the application will compete to perform atomically? Well, it is trying to install the forward pointer in the from space copy. This is an atomic operation that needs to be won by either thread. Either the garbage collector wins or the application wins. In this example, the application won. And therefore, the garbage collector thread discards its copy and says, okay, I lost the race with the application. I need to look at the forward pointer again. I was trying to update it. I lost the update. Give me back the real value that was updated by the application thread and follow that, okay? Now the application can do any read-write on the new copy because this now is the real primary copy of that particular object. And of course, the update reference phase will just move the pointer from the first object to the new copy. All right, Shenandoah comes with a, it's quite tunable. ZGC, in a way, is simpler. It's kind of a simpler garbage collector, especially from the tuning point of view. Shenandoah, I would say that it's more sophisticated from this point of view. You have a lot more choices, of course, a lot more tuning possibilities, and also possibility to get it wrong, but you have to pay attention. So these are the Shenandoah heuristics that you could use. There's an adaptive that tries to maintain a constant free space, a static heuristic that trips a garbage collection every time you pass a certain threshold that you can configure. Compact tries to minimize the memory footprint. Aggressive does back-to-back garbage collection, so as soon as one is finished, another one is immediately started, so you have a continuous cycle of garbage collection going on. And then there's a passive mode where basically all the concurrent phases of Shenandoah are disabled. This basically turns Shenandoah into parallel, but it's very useful if you need to debug things. So for example, you can have problems in Shenandoah that you don't see anymore when you run in passive mode, and that means that there's a problem in Shenandoah. So it's very useful for testing, etc. There's also an additional mode called traversal, where updating references, relocating objects, and marking the objects are done in the same phase. Okay, this is useful because in certain times you can fold in load barriers more efficiently, and therefore it could be a mode that can be tested and used. Again, references. The main developers for Shenandoah are Alexei Shipilev and Roman Kenke from Red Hat. Mailing list is, as before, super quick to answer, super kind. I reported a couple of bugs, asked a bunch of questions. They're really great, so if you want to test them out. So, conclusions. Give concurrent garbage collectors a go. They're awesome. They're really awesome. If you're stuck with JDK 8, your only option is Shenandoah. If you're using JDK 11 plus, you can try either ZGC or Shenandoah and report your feedback. As I was saying, my feedback on this is that I've tested both garbage collector. I can tell you there was very, very impressed. We used to run G1 load test to test Jetty, to do benchmarks of the Jetty behavior, and we got completely different numbers. We went from 30, 50 milliseconds poses that are typical for G1 in certain conditions, and we went down to 1, 2 milliseconds. So that's a 20 times to 50 times improvements in poses with respect to G1. Yeah, it's a Jetty, benchmark. It's very particular to our use case. It may not be the case for you, but I suggest you try them out because they are really awesome. When you have your GC poses in the range of 1, 2 milliseconds, well, basically you don't have anymore any garbage collector problem. It's over, right? You can concentrate on totally other things rather than spending months trying to figure out how to tune your garbage collector. So, yeah, I was definitely impressed. So, try them out. Any questions?